We now turn our attention to the effect of the gravitational field near the surface of the Earth, which is reflected in the value of the acceleration of gravity. Consider a building or any object for that matter near the surface of the Earth. How does one calculate the weight of that object? As we know, the weight is caused by the gravitational attraction by the Earth to that object. If we thought of the Earth as a point mass located at the center of the Earth here, and that's where the building is, then this problem would be rather easy to calculate because you can apply Newton's law of universal gravitation, and you would say F is equal to Fg would be equal to G times the mass of the object times mass of the Earth divided by the distance between them squared and distance radius of the Earth. Right? But we know this is just equal to mg. I mean, you ignore the rotation of the Earth, which is a small effect, and then this will be just the acceleration of gravity. And from that, you can actually calculate the acceleration of gravity. Indeed, you find to be independent of the mass of the object, depends only on the mass of the Earth, and G would be equal to G times the mass of the Earth over the radius of the Earth squared. Now, does that give us the correct value of 9.8 meters per second squared? Well, we can do that. We know what G is. G is 6.67 times 10 to the negative 11 in SI unit, and then times the mass of the Earth, 5.97 times 10 to the positive 24, and you divide this by the radius of the Earth squared. So that is 6.4 times 10 to the power 6 squared. You can easily do the math, and you'll find the answer to be 9.8 meters per second squared. So it reproduces the correct value of the acceleration of gravity near the surface of the Earth. Again, please make sure you understand the difference between small g and big G. Okay, this is small g, the acceleration of gravity, and the big G right here is the universal gravitational constant. These are totally two different things. Okay, so it looks like if we treated the Earth as a point mass located at its center, then you can find the correct expression for the acceleration of gravity on its surface. But how does that make sense? Well, first of all, the Newton's law of universal gravitation deals with 2 point masses. It never talked about how to find the gravitational force between an extended object such as a sphere and another object. Okay? So to go beyond 2 point masses, we have to look at some experimental findings. For example, here we have 3 masses, a red one, a blue one, and a green one. If I want to find the total force of gravity exerted on this green one, how would we do that? Well, Newton's law of universal gravitation deals with 2 point masses at a time. So if you calculate the force between the green one and the blue one, and we call this force, this is the force that we find, we call it F2. And then we also calculate the force given by the red one on the green one, then we have a force like this. Okay, we have a force like this. I didn't draw it well enough. I have to make sure it is aligned with that line connecting the 2 point masses. So here is the line we're talking about. So this we call it F1. Okay, F1 and F2 are calculated from Newton's law of universal gravitation for 2 point masses. Then what is the actual force, the total force exerted on the green mass? Turns out the answer is very simple. All you have to do is to add these 2 vectors. Is to add these 2 force vectors. You get a net force as the vector sum of these 2 forces. Okay, this is the force F. So, very simple. You simply add the forces on this object from all the sources using Newton's law of universal gravitation. This is known as what's called superposition principle. This, you can think of it as an experimental fact, the superposition principle. Okay, very, very important. So that allows us to extend our calculation beyond 2 point masses. For example, what is the gravitational force on this building from the entire Earth? Well, you can think of the entire Earth as made of a whole bunch of point masses. You find the force between each point mass of the Earth and that building. And you add all these forces together as vectors, you'll get a total force. Okay, so that's the principle. But it doesn't answer our question, and that is, how can you replace the extended sphere, which is the Earth, as a point mass located at its center? Apparently, we're getting the correct answer, but why? Okay. Well, it turns out this actually has a reason, and that reason is called Newton's shell theory. Newton's shell theory. Okay. This is actually, there is no, it should be just S-H-E-L-L. Let me cross that out. Newton's shell theory. What does this say? Newton's shell theorem has 2 parts. Okay. Suppose you have a uniform spherical shell of mass m. Okay, of radius r and mass m. So it's empty inside. It's a thin shell with uniform mass distribution. What happens if you consider the force between this shell and a point mass located outside the shell here? Outside the shell. So looking at point mass here. Turns out, according to Newton's shell theorem, the force of gravity between this shell and this point mass is the same as if the shell became a point mass located at center. So you can effectively just take the entire shell and crush it onto one point at its center. Okay, and then the force would be equal to G times mass of the shell, mass times mass of the point particle, divided by the distance between the center of the sphere and the location of the point mass, which is small r in this notation. Okay, again, we replace the entire spherical shell with a point mass of the same mass at its center. Okay, so this is part of Newton's shell theorem. So basically we're saying that f of g equals to what? G m m over r squared. If the point mass is located outside the shell, and that is when r is greater than the radius. R is the separation between the center of the shell and that point mass. Okay, so that is part of it. That's part A of the shell theorem. Part B is when the point mass is now inside the uniform shell. Okay, it doesn't have to be at the center of the shell. It's just somewhere inside. That is the second part of the shell theorem. And Newton's shell theorem in this case tells you the force on that point mass is simply zero. Zero. Okay, so that's the second part of Newton's shell theorem. Zero if R is less than the radius. Okay, that is the second part of the shell theory. And we can understand why the force would be zero if the point mass is at the center of that shell, right? Because if you're at the center, you've been pulled evenly in all directions by symmetry, the force would be zero. But even if you're off center, say you are here, off center, the force on you is still zero. How do we understand this? Well, quantitatively, it makes sense because let's say in this case, we remove the point mass away from the center of the shell, so it's somewhere here. It's closer to that side of the shell, right? It's closer to that side of the shell. Therefore, the portion of the mass on that side of the shell will attract the point mass with greater force because it's closer, right? But on the other hand, you look at the other side, which exerts an opposite force. This other side is further away, so per unit area, it exerts less force, but there are greater areas here, so therefore greater amount of mass, right? So on the left side, you have less mass, but closer distance. On the right side, you have more mass, with longer distance. So at least qualitatively, you can understand why they might cancel each other out. This is not exact proof, of course. Okay, so that begs the question, how does one prove Newton's shell theorem? Well, it is called Newton's shell theorem because it was first discovered by Newton. He actually proved it in his famous book, The Principia. But the proof was very difficult to understand. How do we prove Newton's shell theorem in this modern day? Well, again, we have to use calculus. Okay, some textbooks actually provide this proof at this level, and we don't plan to do it here. This is certainly something doable, but we don't plan to do it here. It takes quite a bit of effort. It's an exercise in calculus, actually pretty good exercise in calculus. What you need to do is to apply the superposition principle. That is, you divide the shell into infinitesimally small point masses, because again, Newton's law of gravitation applies only to point masses. So we have to think of a point mass. Think of the shell as made a whole bunch of point masses here, 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 all these point masses, and find the force between each point mass and that, that red point mass outside. Okay, if you want to find the force in the first case, right? And so you find dF, and then you just sum over, the vector dF using an integral. Okay, more precisely, what you would do is you would cut the shell into rings like this, into a bunch of rings like this. Okay, and you have a ring like this, you have another ring like this, you have another ring like this, and so on. It's doable, but it's not something I wish to really walk you through. It's going to take quite a bit of time to do that. Those of you who are interested, it's an excellent problem in calculus. Now, inside the shell, same idea. We'll be cutting into a bunch of rings, and you integrate to find the force. First, find the force from each ring on that point mass, and then integrate over all these dF. Okay. The reason why I don't want to do this is because there is a better way waiting for us to prove this. When you study physics 8b, when you reach the subject of static electricity, you will find that there is this stunning resemblance between electrostatic force and the universal force of gravity. And that similarity, that mathematical similarity, allows us to find a combined way, the same way of proving Newton's shell theorem for both the electrostatic case and the gravitational case. We'll introduce a new method which would allow us to bypass these complicated integrals and find the proof to both parts A and B of Newton's shell theorem in a matter of 30 seconds instead of 30 minutes. Okay, so that's waiting for us in 8b. Okay, so by the time we reach 8b, trust me, this all be resolved. It's very simple to do that. So we're gonna lead that to the case of electrostatics. Now remember, I said in the very beginning of this chapter that the inverse square nature, that the fact that the force of gravity is inversely proportional to the distance squared, is a unique feature. Okay, this all to the power -2, that power of -2 is mathematically unlike any other power, like -2.1 or -3.4. That -2 is just mathematically unique. You will see that when we study another inverse squared law force, which is the electrostatic force, known also as the Coulomb force. And you will see how we can prove Newton's shell theorem in a very simple and elegant manner. It is totally the result of the inverse square nature of the force. If the force doesn't go like 1 over r squared, if it's 1 over r to any other power other than 1 over r to the power 2, you will not have Newton's shell theorem. Okay, so we'll see that later. So now we're going to just assume that we can accept Newton's shell theorem. And how does one use Newton's shell theorem to study the force of gravity from a spherical Earth to a point on its surface? Well, let's take a look at the case if it's a solid sphere. The Earth is not hollow, right? If it's a solid sphere, let's say it's a uniform solid sphere. What is the force exerted on a point mass from a uniform solid sphere, not a hollow spherical shell? Well, again, it depends on whether this point mass is inside or outside the spherical shell, outside the sphere. Let's say here, first case is outside the sphere, so the mass is here. Okay, the mass is here. How much is the force exerted by this spherical solid sphere, uniform solid sphere on that point mass? Simple. The idea of superposition. Okay, we can mentally divide this solid sphere as a bunch of concentric shells, right? A bunch of concentric shells. So here is one concentric shell that I'm going to draw. All right, right here. This shell is centered at point O. Okay, what is the force exerted by that shell on that point mass? Well, according to Newton's shell theorem, that's equivalent to a point mass at the center of the shell right here. So we can replace this shell as a point mass at the center. And then we can replace another shell as a point mass at the center, and so on. So after we divide this entire solid sphere as a whole bunch of shells, we crash each shell to a point mass at its center, okay, without changing the force given by that shell on that point mass. So that way, shell by shell by shell, the entire solid sphere eventually can be replaced by a point mass at its center. That's the beauty of it. Okay, so whether it's a solid, uniform solid sphere or a uniform spherical shell, if the point mass is outside that sphere, then the force between that sphere, whether solid or a shell, is the same as the force between a point mass located at the center of that sphere and the other point mass outside. Okay, so we have Fg equals g times mass of the sphere times mass of that point divided by r squared. Okay, and it's when r is greater than the radius. Okay, so that result is the same. You cannot tell the difference between a spherical shell and a solid sphere if the point mass is outside. They produce the same exact gravitational pull on that point mass. Okay, now interesting thing happen if that point mass is inside. Suppose you have a solid lump of spherical mass, okay, and you have a point mass somewhere inside of it. You can dig a hole and put something inside. How much is the force exerted on this point mass that's inside? Well, you can now divide the solid spherical region, solid sphere into two regions. One is this shaded area, okay? This shaded area. And this region, relative to that point mass, the point mass is outside this region, right? And when, for this spherical region, if you have a point mass outside of it, as far as the gravitational force is concerned, you can crash the entire region into a point mass at its center. So as far as this shaded region is concerned, how much force does it exert on this red point mass? It's the same as a point mass, the force between the point mass and this red point mass. And that point mass, m prime, is just the total mass, m prime is the total mass of the shaded region. Okay, so that is as far as the shaded region is concerned. And then you have the second region, which is this region, okay, this shell. But the thing is, every point in that second region, if you look at that point mass here, the point mass is inside the entire shaded region here, right? And according to Newton's shell theorem, how much force is exerted on this point mass from the masses in this region? You can think of this region as made a whole bunch of, very thin shells. And this point mass is inside all of these thin shells. Therefore, each thin shell produces a force of 0, right? So you don't have to worry about this region at all. This shaded region, I'm just going to cross all these bars here. The force exerted on the red mass point mass from this region is 0. You don't have to consider m prime. So therefore, Fg equals to G times m prime times m over r squared. Okay, and m prime is a fraction of the total mass. And let's see how much fraction that is. I'm assuming it's a uniform distribution of mass. So therefore, if the shaded region has half the volume of the entire sphere, then m prime would be half of the entire mass. So m prime over the total mass m of the sphere would be equal to v prime over v. V prime is the volume of the shaded region, v is the volume of the entire sphere. And since for a sphere, the volume is proportional to radius to the power 3, right? So I can write this as r to the power 3 divided by big R to the power 3. Okay, so therefore m prime is just m total mass times r to the power 3 divided by big R to the power 3. Okay, that's m prime. And then multiply by the point mass. Now, if we clean this up a little bit, this will give us G m divided by big R to the power 3 times small r, right? This is for r less than r. You see, the force of gravity actually increases as the point mass moves away from the center. In fact, you put the point mass right at the center of a uniform solid sphere, the force of gravity exerted on this red mass will be 0 because it's being pulled evenly in all directions, right? So the force is 0. So as you move away, the force actually becomes non-zero. It actually increases linearly. You can see here, okay, linear. And these two expressions for the force outside and the force inside, they are very different, right? One is 1 over r squared. The other is actually r to the first power. It's a linearly increasing force. But interestingly enough, what happens on the surface? What happens on the surface of this sphere? On the surface, okay, and that is at r equals big R. Okay, these two forces actually become equal. Then because f of g, according to the first expression, is gmm over r squared, right? But according to the second expression, f of g equals what? Gmm small r equals big R, so it's also equal to r squared. See, they become equal. Okay, so I can actually make it equal and equal. And when small r equals big R, the two expressions merge. And therefore, if I were to plot f as a function of r being the separation between the point mass and the center of the sphere, then I get two cases. Case number 1 is a spherical shell. Okay, so for the spherical shell, the force would be 0 inside, right? Would be 0 inside. So I'm going to draw a force of 0 inside. Didn't draw it well enough. And then it jumps to gmm over r squared outside. So it looks like this outside, okay? So this force is gmm. The usual expression of a point, force between 2 point masses. So I would write it gmm over r squared. Okay, so there's a sudden jump for a shell. Okay, this is for a shell. But for a solid sphere, it's a different story. Outside is the same, but inside, the force actually is a linear function, and I can draw this like that. All right, so this is for a solid sphere. So there's a difference. If you dig a hole and get into that sphere, it makes a difference whether the sphere is solid or a shell. The force will be different. But if you're outside that sphere, then you cannot tell whether the sphere is solid or hollow just by looking at the gravitational force, because it's the same. Okay, and interestingly enough, the force actually peaks at the surface of that sphere, no matter what. Okay, so this is how we apply Newton's shell theorem to study the force on a solid, uniformly distributed solid sphere. Now, is the Earth a uniform sphere? First of all, the Earth is not exactly a sphere, but it's very close to a sphere, so we can ignore the anomaly. Secondly, the Earth is not quite close to being to have a uniform density. Rather, if you look at here's a cutaway of the Earth, you have different layers, right? You have just these different layers. Each layer has very different density, so you cannot quite think of the Earth, entire Earth, as a solid, uniform sphere. However, each region, okay, each layer, like this layer, this layer, this layer, this layer. Within each layer, the density is pretty much uniform, and each layer is just a spherical shell of various thickness. Okay, so imagine if you cut the Earth into a whole bunch of extremely thin shells like this, extremely thin shells. Then each shell itself is uniform, right? Even though, they have different density from one shell to another. And because it's each shell is uniform, look at the point mass outside, the point mass here, right? The force from each uniform shell on this point mass, to find that force, I can think of that shell as to be replaced by a point mass at the center. That way, I can once again crash all these shells to the center of the Earth. And therefore, if you want to calculate the gravitational force of the entire Earth on a point mass on its surface, you can then crash every layer of the spherical layer of the Earth as a point mass at its center. So effectively, you can replace the entire Earth as a point mass at its center. No wonder our simplified calculation actually works. Okay, it is really due to Newton's shell theory. It is supported by this theory. Okay, so that's what happens when you look at the gravitational force outside the Earth. Okay, you can safely think of the Earth as a point mass at its center. What if you dig a hole and get into the Earth? What if you are here, for example? You're here. Then the force of gravity is not the same as gmm over r squared. You have to use the analysis that we did here. Okay, analysis we did here, and we have to be also extremely careful because what we assumed here was that it's a uniform sphere. Density is the same, so I can find m prime using a ratio of the volume. But if you have concentric layers of different density in each layer, then it doesn't work like that anymore. But still, Newton's shell theorem still works. All you have to do is to find m prime. This m prime could have a different expression as before. You cannot simply use the ratio of volume like this. But as long as you find m prime, okay, which is the mass that's closer to the center of the Earth than that point mass, you add all these masses up, you still get a simple expression like this. Okay, so that's the power of Newton's shell theory. All right. We also need to talk about another issue, and that is the so-called apparent acceleration of gravity. Now, we know that the Earth attracts an object on the surface of the Earth. Let's say we have an object right here, this object right here. Okay, the Earth attracts it, okay? And the force of attraction is towards the center of the Earth. Okay, that's that mg here. On the other hand, how do you weigh this object? You put it on the scale, right? Or you just here in this case we suspend it from a spring and we read the spring, right? If the spring reads 10 newtons, say, oh, this thing weighs 10 newtons. But you know what? The spring exerts a force like this. That force, is it exactly the same in magnitude as mg? If that is the case, then Fs and mg can simply cancel each other out, right? Because they're already in opposite direction, they have the same magnitude, the net force is 0. Is the net force on the object 0? Well, the object is not moving, but only not moving relative to us. We are moving in a circle. Like everything else. Anything in circular motion would require a centripetal force. Okay, centripetal force. So the net force between mg and fs should not be zero. Rather, they should add up, equaling to what? To this vector here, which is the centripetal force required to do circular motion. Well, this centripetal force is rather small compared with the weight of the object, because after all, this object takes 24 hours to turn this big circle. So therefore, the acceleration is pretty small. But it's not zero, meaning that Fs is not exactly equal to mg. Which one is greater in magnitude? Well, clearly mg, because the net force points somewhat inward, right? And you can see more clearly in this case when you have an object on the equator. On the equator, mg and fs not only are the opposite to each other, but mg is directly, but fs is directly pointing away from the center of the Earth. Okay, so totally opposite to each other. I can write here, I can write mg minus fs equals what? mv squared over r, radius of the Earth. Okay, fs is the reading on the scale. That is your apparent weight. You weigh up the thing on the scale and say, it weighs 10 newtons, therefore you think the thing weighs 10 newtons. It's the apparent weight because it's not equal to mg. mg is greater than 10 newtons because mg minus fs equals to this thing, which is small, but not quite zero, okay? It's not quite zero, right? So therefore, for an object on the equator, the apparent gravity, the apparent gravitational force acting on it as measured by the scale is less than the true gravitational pull. So if you think of Fs as m times g apparent is less than the true value of the gravitational acceleration provided by the Earth on that object. The apparent gravity, in fact, is the smallest on the equator because clearly, here you have a force, Fs is totally opposite to mg, and therefore, to produce that net force will require a smaller apparent gravity, and g apparent here on the equator is 9.77. meters per second squared. Whereas if you are at the two poles here or there, you don't have that problem due to the rotation of the Earth. Okay, you're not doing circular motion. Okay, or you say you're doing a circular motion radius of 0, so it doesn't really do any circular motion. So in this case, Fs is really equal to mg. So this is the reason why at the two poles you have the greatest apparent value of g. So g apparent here is about 9.83 meters per second squared. And going from the equator toward the two poles, g will gradually increase from 9.77 to 9.83. Okay, so there is a slight variation of gravity depending on where you're located on the surface of the Earth. Of course, locally, there are other things that can affect the value of gravity. If you're measuring acceleration gravity with high precision, for example, if you're sitting right above a large oil field, oil has less density than the average density of the Earth, which is 5.5 kilograms per 5.5 grams per centimeter cubed, and that will cause a small but measurable reduction in apparent acceleration gravity in that region. So if you measure the acceleration gravity very accurately and you find that this acceleration gravity in this region is less than what you would expect, then guess what? One possibility is that you're sitting on a large pool of oil. Isn't that nice? Okay, so, but by and large, it doesn't vary by much from location to location. In fact, globally to two sig figures, G is equal 9.8 throughout. All right. So we studied some applications of Newton's shell theorem, and this is very important. Once again, it's an elegant law, elegant theorem, which has an elegant proof, which you will see, I promise, in Physics 8b.